Good afternoon, everybody, and welcome to the lecture number 3 on root locus sketching for the analysis of the stability. So far, we have discussed 2 lectures on the root locus, and this is the third one. And in my previous lectures, we have discussed about the meaning of the root locus. That is the locus of all the closed loop poles inside the S-plane when any system parameters like gain k is varied from 0 to infinite. Then we have started with the procedures or the rules to sketch the root locus. The first rule says that the root locus is symmetrical about the real axis. The second rule says that root locus starts from open loop poles with gain k is equal to 0, and root locus terminates either at open loop zeros with gain k is equal to infinite, or root locus terminates either at infinite with gain k is equal to infinite. So these were the 2 rules that we have discussed in the previous lecture. Let us start with the third rule. The third rule is about knowing the root locus on the real axis. That on which segment of the real axis there is a root locus. So if we know that this is the S-plane and this is my real axis, this is imaginary axis, and this is the entire real axis. Now I would like to know, with the help of rule number 3, that which segment of the real axis is a part of the root locus. So I want to check whether this point lies on the root locus, I want to check whether this point lies on the root locus, and so on. So this rule is only about checking the root locus on the real axis only, not inside the complex plane, not inside the upper half of the real axis or the lower half of the real axis, or neither left hand side of S-plane or the right hand side of the S-plane. So this, after understanding the rule number 3, you will get to know that without sketching the root locus, you will be able to recognize the line segment on the real axis which is a part of the root locus. Now, we should keep this in our mind that the root locus is the locus of all closed loop poles, and the closed loop poles are the solution of characteristic equation. So any point on the root locus, so for example, this is the S-plane and this is the root locus, then any point on the root locus, any random point on the root locus, it will satisfy the characteristic equation. If it satisfies the characteristic equation, means if it has to satisfy the angle criterion and magnitude criterion. So conversely, I can say like this also. For example, that this is my S-plane, and any random point inside the S-plane, let's say this point, any point inside the S-plane, any random point inside the S-plane, let's say this is S1. Now I want to check whether this point S1 is lying on the root locus or not. Then I can check that this point S1 has to satisfy the characteristic equation, or the point S1 has to satisfy angle criterion or magnitude criterion. Conversely, any point on the root locus will satisfy angle criterion and the magnitude criterion. All right. Now, for example, we have one open loop system. So there would be some zeros, there would be some gain, there would be some poles, Of course, these are open loop poles and open loop zeros. Now, if this is given to us, then we can map these zeros and poles inside the S-plane. We know that zeros are mapped by a circle and the poles are mapped by a cross. So let's say, for example, there are one pair of complex conjugate pole. Let's say there is one pole on the real axis. Let's say there is another pole on the real axis, and there is one, let's say, zero here. So a system is having 1, 2, 3, 4 number of open loop poles and 1 number of open loop zeros. Now I want to check that on the real axis, that which line segment of the real axis is a part of the root locus. Now let me identify one point on the real axis. So let's say this is, let's say it is this point. I want to check this point is a part of the root locus or not. So for that I need to see that angle contribution from all the open loop poles and zeros to this point. So I want to know the angle contribution from this pole, the angle contribution from this pole, the angle contribution from this pole, or the angle contribution from this pole, or the angle contribution from this zero. If the total or the net angle contribution from all the poles and zeros, of course open loop poles and zeros, to this point is an odd multiple of 180, then we can say that this point is a part of the root locus. Now, so we are talking about the angle contribution. So this is the angle contribution. To this point it is actually 180 degree. Hey, we know that this is 0 degree, this is pi by 2, this is pi, this is actually pi plus 90, or you can say 270 degree. So angle contribution is always in a anti-clockwise. Okay. All right. Now, angle contribution from this pole is actually 180 degree. Angle contribution from this zero is 0 degree. Angle contribution to this point from this pole is again 0 degree. Angle contribution from this pole, complex pole, to this point is something like this. Let's say theta 1. And angle contribution from this pole is, let's say, theta 2. So we know that this theta 1 and theta 2 both are equal and they are having opposite sign. So the angle contribution from complex pole, this, let's say P1, and complex pole P2 is nullified and it is 0. So the net angle contribution from complex poles or complex zeros maybe is nullified to a point on the real axis. Hence, we don't need to bother about the complex poles or complex zeros for calculating a real point on the root locus. So I don't need to bother about this pole, I don't need to bother about this pole as well. So I need to bother about which are the open loop poles lying on the real axis. Alright. So now the angle contribution, now if you look into this point, to the left hand side, let's say this is the left hand side of this point and this is the right hand side of this point. Now the net angle contribution from real poles and real zeros, I mean this real pole or a real zero or this real pole or this real pole. If any real pole occurs on the left hand side of this point on the real axis, so it is this one, it is, let's say this was P1, this was P2, this was P3, let's say this was Z1, let's say this is P4. So angle contribution from P3 and Z1 is always 0 because they are in the left hand side of to this point. So the net angle contribution from P3 and Z1 is always 0. You can see this is the angle contribution 0 degree. This is the angle contribution 0 degree. But any angle contribution from the right hand side real poles and zeros, here it is P4 to this point, right hand side is P4, so is always 180. So now I need to know how many real poles or real zeros they occur in the right hand side of S plane. So if now we know that the phase criteria is the odd multiple of 180 degree. So now if the sum of the number of poles and the zeros to the right hand side of this point is odd, then that point will lie on the root locus. So to the right hand side there is one pole, one is odd, so this point will lie on the root locus. If let's say for example if there is one zero here, now to the right hand side of this point there is one pole, there is one zero, so there are two number of poles and zeros, so it is even. So now this point will not lie on the root locus. Let's say one pole here, there is one more another pole. So now 1, 2, 3, three number of open loop real poles and zeros to the right hand side of this point. Hence it is odd multiple of 180. Their contribution is odd multiple of 180. Hence this point will lie on the root locus. So there is an easy technique to know whether a given line or a line segment lies on the real axis, which is a part of the root locus or not. Let us take one example. Let's say this is the S plane, this is my real axis, this is imaginary axis, and there is one pole here, one pole here, one zero here, one zero here, there is one zero here, there is one pole here, there is one pole here, and let's say there is one zero here, origin. Now let's identify the segment on the real axis which is a part of the root locus or not. Alright, I want to consider this point, let's say. So to the right hand side of this point, I don't need to consider how many poles or zeros on the left hand side of this point. So 1, 2, 3, 4, I don't need to consider. But towards the right hand side of this point, there is nil, zero number of open loop zeros or poles which are on the real axis. So hence 0 is an even number. So this point is not a part of the root locus. I can still check for this. There is no number of zeros or poles to the right hand side of the, to this point. So this is also not a part of root locus. So I can say that entire this line segment is not a part of the root locus. So I'm giving the legend here. This is not a part of root locus. Now let me check this point. So to the right hand side of this point there is one pole, one is odd, so this point will lie on the root locus. This point, this is again odd, one pole, so entire this segment up to this is a part of root locus. So I will put a legend like this now. This is a part of root locus. Now I will check this point. So to the right hand side, of this point, there is 1 0, one pole. So 1 plus 1, 2 number of zeros and poles. So it is even. Hence, it will not contribute odd multiples of 180 degree phase. Hence, this point is not a part of the root locus. So neither this. So this is not a part of root locus. Let me check this point. To the right hand side of this point, 1, 2, 3. Yes, 3 is odd number. Hence, this point is a part of the root locus. Even this point. So entire this segment is a part of root locus. Now let me check this. So towards the right hand side of this point, 1, 2, 3, 4. 4 is even number, so this is not a part of root locus. This is about rule number 3, that from the rule number 3 we can identify the line segment on the real axis of the S-plane which is a part of the root locus or not. I think it is clear. Let's move to the rule number 4. Rule number 4 is about the angle of asymptotes. Now let us understand what are asymptotes. We know that, let's say there are n number of poles, and let's say there are m number of zeros, and for a proper transfer function n is always greater than or equal to n. So there are n number of open loop poles means n number of branches will start from the n number of poles, and out of those n number of poles, m number of branches will terminate at m number of poles, and the rest n minus m branches will terminate at infinity. This was discussed in rule number 1. So there are n number of branches that will originate from n number of open loop poles, and out of those n number of branches, m number of branches will terminate at m number of open loop zeros, and rest n minus m branches will terminate at infinite. So one thing is clear, that m branches will terminate at zeros and n minus m branches will terminate at infinity. So I don't have problem because there is a special location of zeros, open loop zeros, so the branch can terminate there. But infinity is actually something like this. So all this 360 degree is a part of infinity. All this infinity. This is the infinity direction. So in which direction of 360 degree that n minus m branches will terminate? So that is the question. So to address this question, this is the rule which is known as angle of asymptote. The n minus m branches which are terminating at infinity, they will go along the direction of asymptotes. It means that I'm talking about n minus m branches which are going to terminate at infinity. So let's say this is the S-plane. If I know the direction of asymptotes, let's say this is the direction of asymptote, or this is the direction of asymptote, or this is the direction of asymptotes, then the root locus will move towards the asymptotes, along the direction of asymptotes. So I should know this angle. I should know this angle. I should know this angle. So angle of asymptote will give you the direction of the asymptotes and the direction for n minus m branches which are going to terminate at infinity. So how can we calculate the angle of asymptotes? So there is a rule. It says that angle of asymptotes is can be calculated via this formula, that is 2q plus 1 into 180 degree divided by n minus m, and q goes from 0, 1, 2 up to n minus m minus 1. So let's say we have n is equal to 4 and m is equal to 2. It means that two branches, let's say m is equal to 1, okay. It means that there are 4 branches. Out of that 4 branches, one branch will terminate at 0, and the rest 4 minus 1 branches, which is equal to 3, they will go towards the infinity. So there should be 3 angle of asymptotes. So for these 3 angle of asymptotes, we can calculate like this. So Q here, if n is 4, m is 1, so n minus m minus 1. So 4 minus 1 is 2. So Q will go from 0, 1 and 2. If I put 0 in this equation, then 2 into 0, 0 plus 1, 180 divided by n minus m, 4 minus 1, that is 60 degree. This is one angle of asymptote. Then Q is equal to 1. So 2 plus 1, 3. 3 into 180 divided by 3. So another is 180 degree. Then Q is equal to 2. So 2 into 2, 4 plus 1 into 180 degree divided by 3. Okay. So 360, 60 into 5, which is 300 degree. So 60 degree, 180 degree and 300 degree are the angle of asymptotes. So these 3 angle of asymptotes, they will guide the root locus to terminate at infinity. So this was about the rule number 4, that is angle of asymptotes. Now still there is an ambiguity. What is that ambiguity? So let's say this is the S plane. See, 60 degree asymptote is, this is also a 60 degree asymptote. This is also a 60 degree asymptote. This is also a 300 degree asymptote. Or this is also a 300 degree asymptote. Now root locus will move towards this asymptote or this asymptote or this asymptote or this asymptote. I don't know. So this is also a 300 degree asymptote. This is also a 300 degree asymptote. So which asymptote I need to select? So this is the question. So the next rule will clear this doubt. So the next rule is about centroid. Now centroid is a point on the real axis. Centroid is a point on the real axis where the asymptote crosses. So asymptotes cross a point on the real axis, which is known as a centroid. So if I know the centroid, I can draw the asymptotes then. So before before we draw the asymptotes, we need to obtain the centroid. So once the centroid is obtained, then we can sketch the asymptotes. So centroid is known as minus sigma A. Okay. So centroid is given by minus sigma A. So minus sigma A is given by, the centroid is given by, centroid is on the real axis, A is given by sum of all real parts of open loop poles. Minus sigma A is equal to sum of all real parts, not complex part of the pole. Sum of all real parts of open loop poles minus sum of all real parts of open loop zeros divided by n minus m, where n is the number of open loop pole and m is the number of open loop zeros. So minus sigma A is given by sum of all real parts of open loop poles minus sum of all real parts of open loop zeros divided by n minus m. So if you apply this formula, you will get a centroid. Once the centroid is obtained, now then you can apply angle of asymptotes to sketch the different asymptotes. So now let me take an example. Let's say g of s, h of s is given by some k into s plus 2 upon s into s plus 3 into s plus 4. G of s, h of s is equal to k into s plus 2 upon s into s plus 3, s plus 4. right now I have chosen only the real poles, but you can have a complex poles or complex zeros as well. But we need to consider the real part of that complex pole or zeros. So how we will calculate the centroid? Centroid is given by minus sigma A is equal to sum of all real parts of poles. So I have 3 poles. This is 0, this is minus 3. So what are poles? P1, P2, P3. There are 3 poles. One is at origin, another is at minus 3, then minus 4. How many zeros? Z1 is minus 2. So this is the real poles and real zeros. So the real part of poles, so 0, minus 3, minus 4, sum of all these. So minus 4, minus 3, this is minus 7. Minus. Sum of real parts of zeros. So 0 is minus 2. Upon n minus m, n is 3, m is 1, so 3 minus 1. This will give you minus 7 minus of 2. So minus 7 plus 2, which is equal to minus 5. 3 minus 1 is 2. So minus 2.5 is the centroid. Now once you receive that centroid, then you can sketch the asymptotes. So in our previous example, angle of asymptotes were 60 degree, then 180 degree, then 300 degree, and let's say for example in this the centroid was minus 2.5. So this is how I can start. This is the real the S-plane, and minus 2.5. Let's say this is minus 2.5. Now I can draw a line of 60 degree. 60 degree. This is asymptotes. So 60 degree. Then this is 180 degree, and let's say this 300 degree. So now the 3 branches will move towards this asymptote. See, these are only the guider. Asymptotes are not the part of the root locus. Asymptotes are just giving the guidance to the root locus to move along with the asymptotes. Okay. So the root locus will move like this. It will move along the direction of asymptotes, like this. So on the bank of the asymptotes, the root locus will progress towards the infinity. And at infinity, their gain k is infinity. So let me summarize this lecture. We have discussed actually near about total 5 rules. The rule number 1 is the root locus is symmetrical about the real axis. Rule number 2, that the root locus starts from open loop pole with gain k is equal to 0, and it will terminate either at open loop zeros or at infinity with gain k is equal to infinity. The next rule, the third rule, is that the root locus on the real axis. This can be understood, or this can be calculated whether a point or a part of the line segment is a part of the root locus or not. To do that, to check that, we can always calculate the total number of open loop real poles and real zeros to the right hand side of that point. If that sum is odd, then that is a part of the root locus. If it is even, then it is not a part of the root locus. Then the rest n minus m branches, which are going to terminate at infinity, they will go along the direction of asymptotes, and whose angle of asymptotes can be given by 2q plus 1 into 180 upon n minus m. And the asymptotes crosses the real axis at a point known as centroid, which is given by minus sigma a, which is equal to the sum of the real parts of all open loop poles minus sum of the real parts of all open loop zeros divided by n minus n. So try to understand this. Try to look at the if you have any online books available to you, try to refer those books even, and then we'll have a next lecture number 4, maybe tomorrow or the day after tomorrow. Thank you.